Hey Philip, quick question. I saw in the news that they're now using AI to do some scientific research. Does that mean machines can think? Oh, that's a great question. It's a big one though. How much time do you have? Well, I'm actually kind of busy, so the idea of machines that can perform tasks without any human input has intrigued mankind about as long as we've been building machines. Aristotle, in 350 BC, wrote in his work Politics, "For if every instrument could accomplish its own work, obeying or anticipating the will of others, like the statues of Daedalus or the tripods of Hephaestus, if in like manner the shuttle would weave and the plectrum touch the lyre without a hand to guide them, chief builders would not want servants." This video is the story of how engineers have continuously questioned the status quo on what machines are and what they should be capable of. It is the story of how bold ideas have laid the groundwork for new bold ideas and how these bold ideas have brought us to today. This is the story of thinking machines. When I say thinking machines, you think one thing, the next person thinks another thing, the person right beside you hopefully thinks nothing because you're using headphones like a responsible person. But what do we mean? Lots of people mean different things and lots of people think different things. So for today, when I say thinking machines, I mean computers. And when I mean computers, I mean machines that perform mental tasks. This will make more sense in a little bit. Give us a second. The first computer I want to talk about actually goes back more than 2,000 years into the past. Okay, so now this might not look like what you think of when you hear computer, but the Antikythera was one of humanity's oldest recorded machines that automated a mental task. It was a small mechanical device developed by the ancient Greeks to predict moon phases and ellipses. It was purpose-built to calculate the position of astronomical objects. You couldn't use it to calculate the taxes or even calculate what 5 plus 5 is. If you wanted a machine to do that for you, you had to build another machine, a dedicated machine to calculate 5 plus 5. And lots of engineers throughout history did. Throughout the millennia, loads of very, very smart people built very impressive machines, like a cash register, like an odometer. These are all mechanical machines without any human input. These are single-purpose computers. Every machine could only do one particular task. And that's kind of what machines thinking was like until the Analytical Engine. In the 1830s, Charles Babbage, a British mathematician and inventor, designed a new type of machine. A machine that wasn't designed for one specific mental task. It wasn't even designed for 2 or 3. It was designed for no specific task. If that sounds a little strange to you, then I got you with my deliberately obfuscating language to keep you engaged and continue watching this video. What he designed was a general purpose computer. Let me explain. General purpose computing essentially means that the machine had lots of parts, generic parts, that could perform a lot of different calculations. And using punch cards, little sheets of paper with holes in them that get fed into the machine, one could make the machine do a lot of different calculations in different orders. For those that know what it means and are interested, yes, the Analytical Engine is theoretically Turing complete. These punch cards were essentially the recipe for what calculations the engine was supposed to perform and in which order. This type of recipe is called an algorithm. And although Babbage designed the machine and imagined it to be able and to perform any type of mathematical calculations, I would argue that he lacked the imagination of Ada Lovelace, a fellow mathematician that worked with Babbage on the Analytical Engine and the first person to develop an algorithm for it. She put that imagination into words in her paper of 1843. She said, "The Analytical Engine might act upon other things besides number. The engine might compose elaborate and scientific pieces of music of any degree of complexity or extent." I think Ada Lovelace had a vision beyond what millions of people could imagine computers to do, even only decades ago. While the term itself wasn't invented until 1958, the Analytical Engine essentially separated hardware and software. They have built a machine that wasn't single purpose. They have built a machine now that can perform any mathematical operation that humans can put on paper. As long as we can describe it, the machine could do it. More importantly, it allowed us to perform certain calculations that were never possible or almost impossible with single-purpose computers. That's actually the reason Ada Lovelace chose the algorithm she published. Calculating the Bernoulli number was seemingly impossible. But with the Analytical Engine and software that could do this, it became possible. I know Babbage never actually built this machine physically, but the idea of the machine sparked a new age of how to solve mental tasks, how to automate mental tasks, how to build computers, how to make machines think. Fundamentally, most modern computers still use that same separation of hardware and software that they, in its very, very crude form, invented. Yes, hardware turned from mechanical into electrical, and eventually through the invention of the transistor, turned into electronics and made it very small. Yes, specific architectural decisions allowed computers to get very, very good at certain tasks and optimize certain computers and certain hardware for certain calculations. Yes, pushing to reach Moore's law of doubling the number of transistors regularly has allowed us to reduce the size of transistors down to 4 nanometers. That is 4 millionth of 1 millimeter. Very big numbers and very small numbers are very hard for us to understand. So I want to give you an example. Look at your fingernail. The amount that your fingernail has grown in the last 3 seconds, that's 4 nanometers. I mean, that is small. Yes, software has split into operating systems and higher level applications to make the development and use of it easier. Yes, we've written lots and lots of layers of abstraction into it to make it easier to distribute and reuse parts. Yes, we've written lots and lots of other helpful software that allows us to make the automation of mental tasks simpler, easier, and more accessible to humankind. And yes, we have evolved our interfaces from punch cards and lights into keyboards, mice, screens, and much more complicated and complex input mechanisms like VR headsets and game controllers. I know all of that, but still, considering all of that, computers are essentially still doing the same thing. We have hardware that can do nothing without an algorithm, and then we had algorithms that make those machines perform mental tasks. That is essentially modern day computing. Now we're 2,000 years into history and this long into the video. What does any of this have to do with thinking machines, AI, and where we go from here? AI is a very loosely defined term that I don't like at all, so I'm going to stick with machine learning. Today, I'll be calling machine learning second-order software, and I'll explain why in just a little bit. First, let me explain to you what machine learning is. The idea of machines that can learn how to perform mental tasks rather than being instructed on how to do them is relatively new in human history. It really started with the first artificial neuron that was designed in 1943 by Warren McCulloch and Walter Potts. But the idea of machine learning was really formalized by arguably the most famous computer scientist in history, Alan Turing, in his paper of 1950 called Computing Machinery and Intelligence, where he proposed the learning machine. He explored whether a computer could eventually learn from experience to solve problems rather than following rigid pre-programmed instructions. Let's go back to the difference between the Antikythera and the Analytical Engine. One was custom built to automate a single mental task. The other was built to automate any mental task, but the algorithm it gets fed is custom built to automate a single mental task. We can feed it different algorithms, but we still need to engineer an algorithm to automate a particular mental task. Learning machines explored what would happen if and when we build an algorithm that is like the Analytical Engine, that isn't built to automate any particular mental task, but instead is designed to be fed a certain set of data that will make the algorithm look like a custom-built algorithm and perform tasks that the engineer of the algorithm was never able to mathematically describe themselves. These type of algorithms are called machine learning algorithms. Once the idea of machine learning algorithms became popular, computer scientists very quickly realized that mathematicians had been working on these very algorithms since the early 1800s, because all they needed was approximation functions. Mathematical functions that allowed to look like any other function. Once they used these approximation functions, the field of machine learning was born. Today, you've probably heard of large language models, LLMs, or neural networks, but actually the most widespread machine learning algorithm is something called linear regression. It's a mathematical tool that allows you to approximate a set of data with a linear function. In the 1960s and 70s, linear regression became widely used for commercial purposes. The shift occurred when the mainframe computers like the IBM System 360 became accessible to large corporations for econometrics and supply chain forecasting. Computers transitioned from being purely scientific tools to being business assets that could process large sets of data. Since then, the mathematical models and the underlying machine learning algorithms have become more sophisticated, and they've been able to perform and automate incredible mental tasks. Tasks like playing games, tasks like communicating using natural language, tasks like composing elaborate and scientific pieces of music of any degree of complexity or extent.
Tuesday haze in the rearview glass, another afternoon that's built to last. Street light glows.
Told you, Ada Lovelace was way ahead of her time. Today, these machine learning algorithms are everywhere in our lives. It's likely that the reason you watch this is because a machine learning algorithm decided you would like it and proposed it to you. And if you're still watching, I really hope you do like it. And if you don't want your life to be controlled by machine learning algorithms in the future, then subscribe, like, and make sure that you get notifications so you can decide whether or not you want to watch my videos in the future. Computers have come an incredibly long way since the Antikythera machine. I think we can all agree on that. And it's only been possible because, like I said at the beginning of the video, engineers have constantly questioned the status quo on not only what machines are, but also what they should be capable of. Humans have continuously had bold ideas, and other humans have built new bold ideas on top of those bold ideas. So, can machines think? As always, the answer is, it depends. But I think it's not because we don't know the answer. I think it's because it's the wrong question altogether. We've built machines that can solve mental tasks like we would have never imagined we could. We've used machine learning algorithms in some form or another for more than half a century at this point. But it never bothered us because it just allowed us to progress. It allowed us to be more effective in our day-to-day work. I think the interesting question is not whether or not machines can think. The question is whether or not Aristotle was right. If every instrument could perform its own work, would chief builders still need servants? If machines can do everything that humans can do we still need humans? Till next time, stay silly and follow me.